So, we were discussing our disk and that small object experiment. We had seen the path and now we are trying to do the physics of it and see what kind of path we get from our equations using Coriolis force and centrifugal force. So, we reached up to here, we defined q as x plus I y, and this was q, and then for q we solved this differential equation and we got some solution, and then we put these initial conditions to get those arbitrary constants a and b, and then we finally got the value of q as a function of time, which is here, and from here we can get x and y because q is x plus I y. So, let us first separate the real part of it and imaginary part of it. So, this is equal to a plus I omega a t, and this quantity here is cos of omega t minus I sin of omega t. This is called De Moivre's theorem. This quantity is equal to this quantity. Open the bracket, a multiplied by cos omega t. So, a multiplied by cos omega t, then this I omega a t plus I omega a t multiplied by cos omega t. So, cos omega t here. So, I have done this part, now this part. So, minus a I sin omega t, and then this part I into minus I is plus 1, this I into I is minus 1, and with this minus it is plus 1. So, it is now plus omega a t from here and then sin omega t from here. Okay. So, let us check once again, a into cos omega t is here, then let us say from this side a into minus I sin omega t, a into minus I sin omega t is here, then I omega t into cos omega t. So, I omega a t into cos omega t is here, and this is plus 1. So, omega a t sin omega t. Okay. And this q is nothing but x plus I y. And now you know, if you have two complex numbers with real part plus I times the imaginary part and both sides, then you can equate the real parts and the imaginary parts separately. So, x is equal to a cos omega t, real part only, a cos omega t. This is imaginary part, this is imaginary part, this is real part, plus omega a t sin omega t. Okay, and y is equal to, so leave out this I, omega a t, this is omega a t and cos omega t, and then minus a sin omega t. These are the equations for position, x coordinate and y coordinate as at any subsequent time t. So, these are the solutions of our problem, and dimensionally we can check that everything is all right. A is length, this is length, so A is length, fine. Omega is 1 by time and this time here. So, once again same dimension as A, so fine, dimensionally also okay. So, these are the equations. Now, sketching. So, what I have done is I have made a graph on Excel. I have taken a equal to 1, omega equal to 1, and then for different values of t I have plotted this x and y, calculated this x and y for different values of t, and then I have plotted the graph between x and y, which gives me the path, sketching the path. So, that I will show you now. So, this is that graph, and you can see the nature of the path. It starts somewhere on this x axis, horizontal x axis, 1 it starts, and see how it turns, how it goes away from the origin. The distance from the origin is increasing, and then it is curving, it is curving, it is curving, and then finally it goes towards the edge. So, that is the kind of path we obtain from our equations, and the kind of path on that disc on which I had sprinkled some wheat flour, and then my small ring was going showing the path, they are not very different qualitatively. Yes, so this was the kind of path that I got from on my disc also. So, now I will continue with this non inertial frame little bit, and we will discuss the earth's frame. Normally when we use all kinds of this projectile motion and this and that, we use that lap frame or our road frame or our field frame as inertial. The earth is taken as inertial frame of reference, but I had said that it is nearly inertial, it is not really inertial, because it rotates about its own axis and then it rotates about the sun. So, what we will be doing here, we will be taking account of rotation of earth about its own axis. So, any frame which is fixed on the earth's surface, our lap frame for example, the frame that we use to describe railway stations and roads and trees which are already there. So, we use this surface of the earth as rest, okay, as at rest, and then we set up our x, y, z coordinates there, x, y, z axis there, and then we use it. So, now let us take into account that small non inertiality that is inducted because of the rotation of earth around its own axis. So, one problem that will arise using earth's frame, that when we set up our coordinate axis, the coordinate axes are set up on the surface of the earth. So, our origin is on the surface of the earth. When I was deriving all those equations for equation of motion m a equal to some Coriolis force, centrifugal force, this that, I had taken the origin of this rotating frame on the axis of rotation. But this time the origin of our frame that we will set up in our laboratory for example, that is not on the axis of rotation, that is 6,400 kilometers away, and if earth is rotating, that origin is also rotating about that axis of rotation. So, first let us handle that situation separately, and then we will go to the earth's surface frame of reference. Now, suppose I have a coordinate system and these are the x, y, z axis and this is the origin, and then there is another frame of reference in which here is the origin, and then let us say we have these as this is an inertial frame of reference. Suppose this is an inertial frame of reference, and this frame, it goes around, the origin goes around this point, this origin goes around this point. So, let me draw a circle which is like this. So, this origin goes on this circle, but the axis remain fixed in this frame of reference. The direction of axis remain fixed in this frame of reference. That means, as time passes, as seen from this frame, this is our inertial frame, this is origin, now the origin goes here, but the axis remain in the same direction. It is like this. It is like this. Okay. So, it is something like this. Suppose I have something here and then I am taking it on a circle. See, I am taking it, suppose this is the origin, I am taking this whole thing, go like this, just go like this. What is this? Is it a rotational motion? It is a translational motion. It is a translational motion. At any instant, if I am taking it from here to here in this whole path, suppose I am taking it from here to here, see, all the points are displaced by the same amount and in the same direction. See, part by part, here yes, 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 here yes. So, in any given small time interval, all the points of this are going in the same direction with the same speed, or in any given time interval they are displaced by the same amount in same direction. So, velocities of all the particles, all the points of this frame is the same, and therefore, acceleration is also the same. The acceleration of this origin is same as the acceleration of this point. Acceleration of this origin is same as the acceleration of this point. Acceleration of this origin is same as the acceleration of this point. Or you take any point which is fixed with respect to this frame, the acceleration of that point is also the same. All right, and we very well know what is the acceleration of this. If it is going with an angular velocity omega, and if this radius is r, and if this origin is going, it is not a rotation. So, I will not write this kind of symbol, no, I will not write this. This is not a rotational motion, right. So, this is origin that is going in a circular path of radius r, of radius capital R, with angular velocity or angular speed, angular velocity, fine, for one particle I can always define angular velocity omega. This is it, and hence the acceleration of O is omega square into r towards the center of the circle. Okay. So, the acceleration of this origin is towards the center. When the origin here is here, the acceleration is in this direction. When the origin is here, the acceleration is in this direction, and the magnitude is omega square into this capital R. And all the points, not only this origin, this point also. This is also going in a circle of radius capital R, convince yourself. This point is also going in a circle of radius capital R, convince yourself. The center is not here. For this particle, center is at some different point. This particle or this point, the center is at some other place, but the whole circle is different, but just displaced, and hence the acceleration of all these particles will be same. Acceleration of all these particles or points which are fixed in this frame are same at every instant. As time passes, acceleration will change, but at any given instant, acceleration of this, everything is same, and that is this. So, we will use the law or the rule that we had in the very beginning we had discussed. If a frame is translating with acceleration a naught with respect to an inertial frame, the pseudo force which is to be used in that frame is minus m a naught. So, if a frame is accelerating, is having some acceleration with respect to some inertial frame, and this is our accelerating frame, and it is translation, it is translational motion only, then if this is a naught, then the pseudo force which is to be used on the particle of mass m is minus m a naught. M a is equal to force, resultant force, and minus m a naught. This is the total, applied force. This is force. This is not force, this is pseudo force. So, all the forces are here, and then this is the pseudo force that we are adding in our equation to enable us to use Newton's second law in this accelerating frame, that we will be using for this frame. For this frame also we will be having the same equation, So, m a is equal to total force F and minus m into omega square into this r vector plus here, because you have another minus. This acceleration is inward and therefore, this is outward. I am not calling it centrifugal force, although it looks like centrifugal force, okay, because this is same, this is r. If your particle is here going this way, particle is here going this way, particle is here going this way, particle is here, particle is here. So, if I am seeing from this frame, then the same force m omega square r is to be used. In centrifugal force, distance of the particle from the axis. For different particles, it is different. So, this will be added if the origin is translating. And then once again we come to the Earth's frame of reference. If we have Earth and then we are somewhere here, so I can always reorient. So, we are somewhere here, this is the axis of rotation, north south, geographical north south, and say this is the rotation. In that case, our origin is here and we fix up our axis system maybe this way, maybe this way. This is vertical, okay, this is vertical, this is horizontal, then perpendicular horizontal, two horizontal axes, one vertical axis. Now, as time passes, the earth rotates, this origin is going in a circle. This origin is going in this circle, this whole earth is rotating. So, this origin is going this way, this way, this way, this way, this way, this way, and here is the center. So, one thing is that origin is rotating, is going on this circle. Another thing is the direction is also changing. The whole earth is rotating with respect to this about this NS line, and this is fixed with the earth. So, this is also rotating. If the whole earth is rotating, this is also rotating. So, if this is here, when it comes here, this will be going like this. This line will be here. This line will be here. Similarly, this line will be somewhere here and that line will be somewhere else. So, it is also rotating with respect to this axis. This is the axis of rotation of my frame and the angular velocity is omega. So, those Coriolis force and centrifugal force will be there. On top of this, this kind of force will also be there. So, what we will write? We will write mass times acceleration. Now, I am using this frame which is fixed on the earth's surface and I am seeing some particle m which is going with some velocity v, some acceleration a, as seen from this frame of reference, that a is here. Mass times acceleration is equal to total force. This is the total force applied, real forces, and then I have minus or plus this quantity. This is plus m into omega square r vector. What is this r vector? This r vector is from this origin. This origin is going on a circle, and then the center of the circle and the position of the origin, that is r vector, capital R vector here. So, here it will be, if I am here, then this is the circle, this is the center of the circle, here is the origin. So, this is r vector, this is r vector. And if I use this capital R for the radius of the earth, then this r vector is here, but let me not write it r, because r I will be using for the radius of the earth. So, whatever this particular vector, any vector you write here, so this vector and in this direction, that I have to write here. So, this will be if I call it some say E cap, okay. It is perpendicular to this ns axis wherever this origin goes. So, this will be m omega square. Now, okay, little bit of geography. This is our equator here, and then if you are somewhere here on the earth, you are on the equator, and we say that the latitude is 0. Okay, the latitude is 0 if you are here, and if you are above the equator, then this angle, how much above you are going, is known as latitude. This is the latitude, and then 90 minus this, which I write lambda, is called co-latitude, and I will be using this co-latitude. This lambda is co-latitude, and what is that lambda? If you are somewhere on the surface of the earth, join that to the center and see what is the angle of that line with the axis of rotation of the earth. That is lambda, known as co-latitude. In geography, more commonly used angle is latitude, which is this angle here, and the relation is lambda and theta, they add to 90 degrees. So, this is co-latitude. So, sine of lambda, capital R into sine of lambda, and then in this direction, in this E cap direction. So, that comes from the shift of the origin, rotation of the origin, and then rotation of the frame. Those things will be there, minus m omega cross r vector and minus 2m omega cross v. This r vector is the position of the particle. If the particle is here, then from the origin you join this as r vector from your origin. If I am setting my axis system here, then whatever origin I choose from there, what is that r vector, that is here, and what is the velocity as seen by my frame, that is here. This is our Coriolis force, this is our centrifugal force, and this is a constant as far as the particle is, only mass of the particle is here. Otherwise, the position of the particle, the velocity of the particle does not matter. And if I am writing acceleration, if I am dividing by the mass, this mass also goes, and then this quantity is just constant. So, and also if I am using this earth surface and I am looking at some particle which is moving under some forces, then the gravity is always there. So, m times g will be always there, and then you have this and other forces, okay, other forces. If you are only looking at the motion under the gravity, then this will be 0, and then other things, all these things, m omega square r sine lambda E cap minus m omega cross r, all these things will be there, and minus 2m omega and then cross v, all these things will be there. What I am doing is this quantity and this quantity, this is independent of the position of the particle, velocity of the particle, acceleration of the particle, and therefore, these can be combined. You can take m out. If you take m out, this will be m times g and plus m omega square r sine lambda in E cap, and this is just a constant, does not depend on anything if m is taken out, and this we will call G effective. This we will call G effective. So, this will be absorbed in G, and these two terms taken together we will call G effective. So, m times G effective, any other forces if present, and then the centrifugal and this Coriolis force. This will be our equation of motion, and we will be using this equation for some simple cases. a freely falling particle or maybe a projectile and so on.